Okay, so let's start. I think from now onwards, certainly today we will take the break, not the break, I mean the discussion session at the very end, so that we would have covered what we intend to cover. Not much today also. So last time we did the global Cauchy theorem and also introduced the notion of homotopy, which many of you have seen in your algebraic topology course already. Anyway, we introduced it. And we said today we would like to do that homotopy implies homology. If two closed paths are homotopic, then they are homologous. Okay, so as preparation, we did a small lemma, small observation, and we will make use of that and do this today. It doesn't take so much time, but I'm going to go slowly, so we will take some time to do it. And then we will start residues. So residues also you have seen in your last course. We will do the residue theorem and continue from there onwards. And then we will stop and discuss whatever you have to discuss. So today there will be one assignment question, which will come sometime in the slide, and just one question, and you have to submit it exactly like last time via Google Forms, and the deadline is sharp 12 noon lunchtime tomorrow. Tomorrow is Saturday. Yeah. Okay. I will close the form sharp at 12 tomorrow afternoon. Noon, and I won't open it again. Okay. So this time, anyway, last time all of you knew how to submit it, so I expect no trouble this time. Okay, all right. Last time we did global Cauchy theorem, basically, and let's go to the slides and recall, and then continue from there onwards. Start sharing. Yeah, is the slide visible? Slides are visible?
Yeah, it's visible for me.
Visible? Okay. Yeah. So let's start. Today's topics, I have written homotopy and homology, but we are not going to do all that. We are just going to make one statement that if two closed paths are homotopic, then in your region omega, then they are homologous. Homologous means what? Gamma 1 and gamma 2, two cycles are homologous if for every alpha outside omega, the index of alpha with respect to gamma 1 equal to index of alpha with respect to gamma 2. So if gamma 1 and gamma 2 are homotopic, we want to conclude that and conclude this, and then we will move to the residue theorem. Okay, so let's recall last time what we did. In the last class, we proved the global Cauchy integral formula, and as a quick corollary, the global Cauchy theorem followed. So quickly recall what was this. If f is holomorphic throughout omega, then this is what is called the Cauchy integral formula. So f at a point times the index of that point. So what is gamma here? Gamma is a cycle, meaning a formal sum of closed paths. And the condition on gamma is, for this formula to be valid, the condition on gamma is it should be homologous to 0. So such a formula is true whenever gamma is homologous to 0 in omega. And recall homologous to 0 in omega. For every alpha outside omega, for any point outside omega, say alpha, index of alpha with respect to gamma should be 0. What is index of alpha with respect to gamma? It is this kind of an integral, but there is no FW. It is dW by W minus Z. That is the index. And for every point outside omega, the index has to be 0. Then you say that gamma is homologous to 0. So your region has no further restriction, and the only restriction on gamma is it is homologous to 0. So a small topological condition, and then you have this formula. So Cauchy theorem was an immediate corollary to this, because if you have this small f which is holomorphic, you take capital F to be f minus, take a point A and take f minus A, no, z minus A times f of z. If you take that function to be capital F, of course that's holomorphic, product of two holomorphic functions, z minus A and f of z, and you apply this formula to that capital F. So you will get capital F of A at A times some index, but capital F at A is 0 because z minus A is 0 at A. So this part becomes 0, and what will be this part? F of W is W minus A times small f of W by W minus A, so that cancels. So the right hand side is just integral of FW dW and left hand side is 0. So the Cauchy theorem follows from the Cauchy integral formula quite easily. So this is what we proved, and what was the main idea of the proof? So I told you this is proof from Rodin's third edition, where he attributes the proof to John Dickson, and I said it's a relatively new proof because most of the things that we are doing is from a century ago, but this is recent, 1971. And the main idea of the proof was you consider a function of two variables. We called it G. Case by case it was defined fw minus fz by w minus z whenever w not equal to z, and when w equal to z, you take it to be f prime w, which is same as f prime z, w equal to z. And then the first observation is this function is continuous on, it's a function of two variables, this function is continuous on omega cross omega. And then you integrate this along the cycle gamma, and this integral makes sense. It's well defined because of the continuity of G. You're integrating with respect to one variable, let's say W. So G of ZW dW, integral of that. And that defines you a function in Z. So we called it h of Z. So h of Z is well defined because of the continuity of G. In the variable W, we use a continuity. And so you have got this function h, and the first step was to show that h is continuous, which we showed by showing that if Zn converges to Z, then h of Zn converges to h of Z. So that showed the continuity of this function h. And we observed that if we can show that h is 0, whenever h is 0 on omega minus gamma star, then this formula follows. H equal to 0 on omega minus gamma star is exactly this formula. So what we are going to show is, in fact, h is identically 0 on omega. H is defined on omega, and we will show that h is identically 0 on omega, and in particular this formula will follow. And what was the idea to show that h is identically 0 on omega? Right now h is a function, and we showed continuity. And by Fubini's theorem together with Moreira's theorem and Cauchy's theorem, we showed that h is holomorphic throughout omega. And the next step was to extend h analytically throughout C. So you have got an entire function which restricts to h on omega. And then we showed that that entire function, the way we constructed, is bounded. So by Liouville, it's a constant. And we could also evaluate the constant, and the constant was 0. So therefore, this entire function is identically 0. So restricted to omega is the function h, which is identically 0, which is exactly this equality. This was the proof. So it's a very elegant proof, simple and elegant proof, conceptual. So this was the main idea, and then we discussed homotopy. Today we will show that if two curves are not curves, two closed paths are homotopic, then they are homologous. And then we will move on to the topic of residues. Just start and prove the residue theorem, and the rest we will do from the next class onwards. Okay. So this is the agenda for today. So let's start with homotopy implies homology. Suppose gamma 1 and gamma 2 are omega homotopic closed paths in a region omega. So what does this mean? Recall the definition. There exists a continuous map, continuous H from the unit square to omega, such that at time t equal to 0, it is the first curve, gamma 1, and at time t equal to 1, at the end time, endpoint, it is the curve gamma 2. So h of S0 is gamma 1s, at the starting it's gamma 1, and h of S1 at the ending it is gamma 2, and h is also taken to be closed. So h of 0t equal to h of 1t for all t. So all these continuous curves are also closed. Okay. So at the starting it's one of these paths, ending it's the other path, and it can be continuously deformed within omega via these closed paths. That's what homotopy meant for us. And we want to show that the index of alpha with respect to gamma 1 equal to index of alpha with respect to gamma 2 for every alpha outside omega. This was the definition of gamma 1 and gamma 2 being homologous. So this is what we should show. We are going to make use of the observation from the last class. You remember, after introducing homotopy, we proved a small lemma, which was that if you have two paths, gamma 1 and gamma 2, and if alpha is any point from C, we proved that if mod gamma 2 minus gamma 1 is strictly less than mod alpha minus gamma 1, right? Mod gamma 2 minus gamma 1 is strictly less than mod alpha minus gamma 1, where alpha is some fixed point from C. Then we showed that the index of alpha, this point alpha with respect to gamma 1 equal to index of alpha with respect to gamma 2. This is what we are going to use. So here you have two paths, gamma 1 and gamma 2, and you want to say that the index of alpha with respect to gamma 1 is index of alpha with respect to gamma 2. So if alpha is such that mod gamma 2 minus gamma 1 is strictly less than mod alpha minus gamma 1, then you are done by the previous observation. But this may not happen. This condition may not be met, and then what we are going to show is you can, using the homotopy H, you can construct finitely many paths in between. So gamma 1 can be continuously deformed to gamma 2. Using this idea, we are going to construct in between a number of paths such that this distance condition, mod gamma 2 minus gamma 1 is strictly less than mod alpha minus gamma 1. Whatever alpha you give me outside omega, this condition for alpha can be met for successive things. So this result on homologous to each other, index of alpha with respect to one is index of alpha with respect to the other, can be done at every two stages, at each stage. So suppose you have constructed, some number of curves, alpha, beta 1, beta 2, etc. up to gamma 2. Then from gamma 1 to beta 1 indices are same, from beta 1 to beta 2 indices are same, etc. Beta into gamma 2 indices are same. So you can pass on this information from at each step and prove this result. This is what, so it's a basic idea. It's an easy enough idea. We will execute this. So, so this was the observation that induced alpha, not induced, index of alpha with respect to gamma 1 is index of alpha with respect to gamma 2 if mod alpha minus gamma 1s is strictly bigger than mod gamma 2s minus gamma 1s for each s. S is from the interval 0, 1. So for each s between 0 and 1. Okay, so this is what we will do. So we are starting the proof. First observation, H is continuous, right? H is continuous from where to where? From unit square, 0, 1 cross 0, 1, compact 0, 1 cross compact 0, 1 to omega. And it's continuous, and this unit square is a compact set, therefore it is uniformly continuous. Okay, so what is uniformly continuous? For every epsilon, I have a delta such that something implies this thing, but the delta does not depend on the points. Whenever mod x minus y is less than delta, mod fx minus fy is less than epsilon. The same delta works throughout the set. So that's uniformly continuous, and because of this, for every epsilon, there is a delta. My delta is going to be 1 by n here. So there exists an n such that if this condition is satisfied, mod s minus s prime plus mod t minus t prime is less than or equal to 1 by n, then modulus of h of st minus h of s prime t prime, that is strictly less than epsilon. So you want distance to be less than 1 by n implies this, but if this is less than or equal to 1 by n, then the distance between those 2 points is also, the usual distance between those 2 points is also less than or equal to 1 by n, right? Between s comma t and s prime comma t prime, the usual distance is less than or equal to this distance. Therefore, uniform continuity in particular will give you this. Okay. So now you note that if you take h of s comma k by n and h of s comma k minus 1 by n, then these 2 points, right, s comma k by n, s comma k minus 1 by n satisfies this condition. S minus s is 0 and k by n minus k minus 1 by n is 1 by n. So it satisfies this condition. Therefore, if you take these 2 points, then obviously this modulus is less than epsilon. For any epsilon, there is an n such that you get this. Okay. So suppose you take these curves, right? These are continuous curves, no? These are the curves giving you the homotopy. So these continuous curves CKS, suppose you call HS at K by N to be CKS, then these are closed curves. And what is C0? C0 is the starting point gamma 1, starting curve gamma 1, and Cn is the ending curve gamma 2. So if you are going to choose epsilon to be strictly less than the distance of alpha, right? Alpha is given to me and I have to show that the index of alpha with respect to gamma 1 is equal to index of alpha with respect to gamma 2. Suppose you choose epsilon here. For every epsilon you have an n such that something happens, and suppose you choose this epsilon to be strictly less than distance of alpha from the image of the unit square under H, and alpha epsilon to be strictly positive, then what happens? Then you notice that, so this is what, this is modulus of ck minus 1, right, at s. Cks minus ck minus 1 s is less than epsilon, and if distance is bigger than epsilon, then alpha and any curve ck, alpha comma cks, the distance is bigger than epsilon. So you are getting cks minus ck minus 1 s modulus is strictly less than modulus of alpha minus ck minus 1 s in particular. So this was the condition of the lemma. If this is true, then the index of alpha with respect to ck and index of alpha with respect to ck minus 1, they coincide. So by taking, how many curves have I taken here? For this epsilon, I have chosen this n, and then I am taking C0, C1 up to Cn. So n plus 1 many curves. And if I have these n plus 1 many curves for successive 2 curves, the condition of that lemma is met. That mod ck minus 1 is strictly less than mod alpha minus ck minus 1. And therefore the index of ck minus alpha with respect to ck minus 1 is same as the index of alpha with respect to ck minus ck. And since the starting thing was gamma 1 and the ending thing was gamma 2, it shows that index of alpha with respect to gamma 1 is equal to index of alpha with respect to gamma 2. So if we choose epsilon like this, then the lemma is applicable to all the ck's. If the lemma is applicable to all the ck's, right? If we could apply that lemma to all the ck's, then we are done. Is this point clear to everybody? Is there a doubt here? So if you choose an epsilon like this, you have taken an alpha, and if you take an epsilon strictly less than this distance, then you are manufacturing, then you are getting that alpha, the distance to the curve, distance to this curve is strictly bigger than this. So by the previous observation, indices will be the same with respect to this curve and this curve. And the starting thing was gamma 1. So gamma 1 and the next one, C1, indices are same. From C1 to C2, indices are same. C2 to C3, indices are same, etc. all the way up to gamma n. Therefore, gamma 1 and gamma n indices are same. Okay. So if the lemma was applicable to all the CKs, then we are done. And I explain why. Because successively you can pass the indices information. But let me ask you this question. Why is this, see, I want to choose an epsilon positive, right? And I want epsilon to be strictly less than this. That means this has to be strictly positive. Why is this true? Why is this distance strictly positive? Can someone tell me?
Because the image is compact and alpha is not in that image.
Correct. Because unit square is compact and h is continuous. Therefore, h of the unit square is compact and distance is a continuous function. Therefore, it takes a minimum there and therefore it's strictly positive. Alpha is outside, right? Alpha is outside omega and h of unit square is inside omega. And because it's compact, there's a positive distance, so that can be done. So everything is okay. This would have been the proof, but not quite because of this sentence. I wrote here that if the observation from the last class, which is that lemma, is applicable to all the CKs. So there's a question here, right? It is not quite applicable to all the CKs. Why is that? Can someone tell me? The lemma that we proved is not really applicable to these CKs as we have done it. Why is that? What was the proof of that lemma? So if gamma 1 and gamma 2 are there with that condition, then I think you were arguing with, so you would take the new curve, new path, so gamma 1 and gamma 2 were paths, and then you would take the path gamma 2 minus alpha by gamma 1 minus alpha. Call it gamma, and then you looked at gamma prime by gamma and integrated that. That's what gave you the result. So all this index and the definition of index as well as this proof, all these use, see what is index? Index is integral of dw by w minus z, right? Over your path. So that it's a path was used, in parameterizing. So what is a path? That's piecewise continuously differentiable. So that is used in defining the index and also in proving this observation, proving that lemma. But what is CK? CK is h of sk by n. H is continuous. So therefore these are curves. But h need not be differentiable. So these need not be paths. So the definition of the index as well as the observation about transferring these indices, these are not quite applicable to CKs. Therefore, this is not quite a proof. The idea is good, but this is not quite a proof. So we have developed the notion of index and the results about this notion for a closed path gamma or a finite formal sum of those, which we call a cycle, and not for a curve. Continuity was not enough. We wanted piecewise continuous differentiability. So one way out is to develop all these notions for curves. So that can be done. You can define the index for a curve by doing some approximation using piecewise differentiable curves, etc. And you can prove that lemma also. So this is an exercise in Rodin that you can develop these notions for curves. And once we do that, our previous slide is correct. It can be made correct. I mean, it can be interpreted to be correct. And then we are done. Another approach is to tweak the above argument a little bit, which is what Rodin does in the textbook, in the text part of it, not in the exercise, and that's what we will also do. So we are going to tweak the argument a little. So remember, the only problem was that the CKs are not paths, they are only curves. So we will, construct some paths which are very near to this curve CK, and that will take care of it. So observe also that, so last time we made use of this observation that if I put k by n and k minus 1 by n and s constant here, that's less than epsilon, but I can do the same thing with the variable s by fixing t. So observe that second variable you keep fixed t, and the first variable if you take j by n and j minus 1 by n, then of course the distance between these 2 points is 1 by n, and therefore this modulus is also less than epsilon. And the problem earlier was that these are only curves and not paths. So what you do is you approximate these curves by nice paths. So you take this n plus 1 many points on these curves. This is a continuous curve, closed curve, continuous closed curve. And you take n plus 1 many points like this. So CKS is HSK by n. You take these curves and you consider the polygonal paths PKS. So what is PKS? PKS you are going to form by joining these points, right? This is your curve. You have considered n plus 1 many curves. Let us say CK, K going from 0 to n. So n plus 1 many. And given a curve CKS, you're going to take n points on that curve and join them by straight lines and make these polygons on that curve. Okay. And I will choose the points at correct distances. I will take h of 0 comma k by n, h of 1 by n comma k by n, h of 2 by n comma k by n, dot dot dot, h of 1 comma k by n. So how many points are there? N plus 1 many points. And h1 comma k by n is same as h0 comma k by n because these are closed curves. So these n plus 1 many points you join by straight lines and you get a polygon. So you take this polygon, you take this polygon. Now you have got a path, right? I have underlined path because these are polygons. So piecewise they are continuously differentiable because piecewise they are just straight lines. And let me do this joining at the correct speeds, so to say. What do I mean by this? With the right speeds, what I mean is I want to compare with this thing. So as s goes from 0 to, see, s is going from 0 to 1, right? H is from the closed interval 0 to 1. As s goes from 0 to 1 by n, I am going from this point to this point. And s goes from 1 by n to 2 by n, I am going from this point to this point. So I am adjusting the speed of my path. Okay, 0 to 1 by n as s goes. So at s equal to 1 by n, I am at this point. And I control my speed so that at s equal to 2 by n, I am at this point, etc. Okay, so my straight lines are like that. At s equal to 0, I am at this point. At s equal to 1 by n, I am at this point, etc. So with these control speeds, if you join the polygons, then observe. So this is what you have. So now you have this continuous curve, closed curve CK, and then this polygonal paths PK. And observe that these PKs are very near to CK. In fact, the distance between PK and CK is less than epsilon. The distance between PK and CK is less than epsilon. Why is that? Is that obvious? Because take for example here, the line joining here, right? The line joining here will be this times 1 minus t plus t times this point. And then you have CK at the correct distance, at the correct this thing s going from t to 1 by t. So if you take the straight line joining this and if you subtract, and I told you this is as s going from 1 by n to 2 by n. So here also I am taking s going from 1 by n to 2 by n. So if I subtract, so a point here will be the straight line joining these 2 points, and a corresponding point there will be h of s comma k by n. So if you subtract, because of this condition, the distance between these 2 points itself is less than epsilon, and if you have a point in between, you will get that distance also to be less than epsilon. Is that clear? Right? The straight line joining these 2 points is of the form 1 by this point times 1 minus s plus this times s, and my s is going from 1 by n to 2 by n. So as s goes from 1 by n to 2 by n, if I subtract this straight line from this curve, what do I get? I get, so this also I can write it as hsk by n times 1 minus s plus hsk by n times s. Okay, so when you subtract, you will get this minus this times 1 minus s plus this times this minus this times 1 minus s. This minus this times 1 minus s plus this minus this times S. But both these things are less than epsilon, so you will get less than epsilon times 1 minus S plus epsilon times S, which is epsilon. So this follows. And you can also observe that pk plus 1 minus pk is also less than epsilon. That's also obvious. So if you take line joining these two and line joining these two, and if you subtract, again from this it will follow that that's also less than epsilon. So please check that. So you will get this is less than epsilon and this is also less than epsilon. Now we can apply the previous lemma to pk's, right? So what all? So I would like to choose my epsilon so that alpha minus pk, that distance should be bigger than alpha minus pk plus 1, right? So pk minus 1, the distance should be strictly less than alpha minus pk minus 1. Then I can pass the indices information from one to the other. Okay, all right. So can you tell me what should we choose? So I would like this distance should be strictly less than alpha minus pks. That's what I want. So alpha minus pks should be strictly bigger than epsilon. So you have to choose epsilon such that alpha minus pks is strictly bigger than epsilon. Then you can use that lemma and pass on the indices information. So what we do is, maybe the epsilon that we have chosen earlier may not work. This may not work, because this only made sure that for C case you have that thing. Now there's a further approximation between CK and PK, that also we need to take care. So instead of this, you take 2 epsilon. That will do the job. Okay, so if you take 2 epsilon to be strictly epsilon such that 2 epsilon is strictly less than this, then it follows that alpha minus pks modulus is strictly bigger than epsilon. Why is that? So this finishes the proof. Why? Because now you are passing the information, right? So alpha minus pks is strictly bigger than epsilon. So this distance is strictly less than mod alpha minus pks. So index of alpha with respect to pk is equal to index of alpha with respect to pk plus 1. So between the curves pk, you can pass on the indices information, because pk's are paths and therefore the lemma is indeed applicable. So between pk to pk plus 1 you can pass the information, and between c0 and p0 also you can pass the information, and between pn and cn also you can pass the information. So what you are doing is c0 to p0, then p0 to p1, p1 to p2, etc., pn minus 1 to pn, and then pn to cn. But c0 is your first curve gamma 0, gamma 1, and Cn is your last curve, last path gamma n. So you have passed the information. So this finishes the proof. So it's just that basic observation which gives you homotopy implies homology. By the way, why do you get this to be strictly bigger than epsilon if you choose like this? That's obvious, because if mod alpha minus pks is less than or equal to epsilon, then what happens? Then alpha minus cks will be less than or equal to alpha minus pks plus pks minus cks. Triangle inequality, if you apply, you will get less than or equal to epsilon plus epsilon. You will get less than 2 epsilon. So you will get alpha, distance between alpha and cks. Cks is a point inside this, okay? So if this was less than or equal to epsilon, you will get the distance between alpha and ck to be less than or equal to 2 epsilon, which is not true. It is bigger than 2 epsilon. So only way out is this. So this follows because of this 2 epsilon and triangle inequality together with this inequality that we have. Is the proof clear? So the idea was to use these homotopic curves in between, but the only problem was they were only curves, not paths. So what you did is one more approximation using these polygonal paths and then transfer the information. So basic idea is quite simple. Here is a question which bothered me for a minute, and therefore I thought I'll ask you also. Is it necessary that these polygonal paths are, see this the curves HK, right? The curve CK, which is H of S comma K by N. These are of course inside omega, because H of unit square is inside omega. Inside omega, you have these homotopic curves, and then you are taking these n points on each of these curves and you are joining it by polygons, polygonal paths. Is it necessary that these polygonal paths are inside omega? So let me leave it as a question. We will, I will ask you in our discussion session at the end. Okay, question is clear, no? We are approximating these curves CK using these polygonal paths. CKs are inside your region. Is it necessary that these polygonal paths are also inside your region in this proof? Okay. So here is the assignments, and as I told you, the deadline is sharp noon, 12 o'clock tomorrow lunchtime. Okay. So what we have proved is homotopy implies homology. If two paths are homotopic to each other in omega, then they are homologous in omega. So is it true? Is the converse true? So I am telling you converse is not true, which means there are paths that you can construct which are homologous but not homotopic. So there are paths. So what you have to do is, to give an example, construct a path such that for every alpha outside omega, index of alpha with respect to gamma 1 is equal to index of alpha with respect to gamma 2. But gamma 1 is not homotopic to gamma 2. Okay, so this is the assignment. And as I told you last time, if I suspect copying, I will report it. Okay, you can't copy. You can't copy from each other. If you copy from the net or somewhere else, then you have to understand the argument and you have to tell me your source. Okay, and it has to be in Google Forms. Please do not email me anything. Okay, no PDF files, nothing. If you email, I won't check it. It has to be on Google Forms, and it has to be submitted by tomorrow. Remember to sign out of your personal Gmail and log in via LDAC. Only then you will be able to submit. And since you could do it last time, I hope this time you can do it without trouble. And don't tell me that you cannot do it. You have to find out how to do it, and you have to do it. Okay. So last time I spent a lot of time helping you to do it, but you should have learned by this time. Okay, fine. So let's go to the next topic. So, and briefly explain your example. Don't write too much. It has to be brief. So you have to give an example and you have to briefly justify why these two cannot be homotopic and why they are homologous. No need of each step-by-step description. I just want to understand that you have got the basic idea. When we have a real exam later, maybe I'll ask you to explain some of these questions with full details, but not right now. These are just to make sure that you are following the course and you are also working a little bit towards this course. So let's start discussion of residues and residue theorem. So recall from your last course 412, what is a meromorphic function? So f defined on an open set is said to be meromorphic if its only possible singularities are poles. So your function now may not be holomorphic, it may have singularities, and we would like the singularities to be isolated. Not just that, we would like them to be poles. Only possible singularities are poles. So something like e power 1 by z is not meromorphic because z equal to 0 is an essential singularity. Though it's isolated, it was essential. So pole meaning, I mean, only poles are allowed, then it's called meromorphic. So note that set of poles of a meromorphic function, so let's call it P of f. You remember z of f was the zeros and P of f is poles. This has no limit points. So zero set has no limit points. We had to give a proof, which was not so obvious. You know, we had to use connectedness, and then we had to show that set of limit points is both open and closed, and then somehow we had to show that it's non-empty if the function is not constant function 0. But here it's obvious, no, set of poles has no limit points. Why is this? because these are isolated, right? So if you have a pole, then it's an isolated singularity. So in a small disk around it, there is no other singularity. So if there was a sequence of poles converging to that, then there will be a small neighborhood in which there will be another, right? If Z was a limit point and a pole, then there will be a small neighborhood of Z in which there will be other poles, right? At least another pole, but that's not allowed because it's isolated. So a set of poles has no limit points as kind of automatic from the definition. And also PF is countable. Earlier we said that zero set is countable. Same argument shows that PF is also countable. Can someone quickly recall why will PF be countable? Same principle. Zero set was countable, ZF was countable, same argument shows that PF is countable. So the point to notice is that omega, so what is called compact exhaustion. Omega can be written as a countable union of compact sets. By the way, I never gave a proof of that. I have used this once before. If you take omega, your region, then it can, or open set, open domain, it can be written as a union of compact sets. It requires a proof, and I have not done it. I assume you might have done it in 412, otherwise you should do it. Okay, so once you can do that, then it follows that this set is countable because in each, so you can write it as a countable union of compact sets. In fact, you can write it as a countable union of increasing nested compact sets. And in each of these compact sets, because of no limit points, it will be a finite set. In each of the compact set, there will be only finitely many poles. And because it's a countable union of compact sets, it's countable. So compact exhaustion. So recall when we classified the singularities, we had removable, we had pole, we had essential. What was our definition of pole there? The definition was that you have a what is called the principal part, right? You had C1 by Z minus A plus C2 by Z minus A square plus etc. finitely many such terms. So you had something like at each pole A, you have a rational function of this particular form. Summation 1 to m, a finite part, a finite number m, ck by z minus a power k, such that, what does this mean? This means that f minus q, if you subtract this part out of f, then that is a removable singularity at a. In other words, it's holomorphic at a. It can be redefined so that it's holomorphic at a. This was the definition of pole. Now we are going to define the residue of f at a. So at each pole you have a residue, and what is the definition? So by definition, this residue is, and we denote it by res f semicolon a bracket, is by definition the coefficient of 1 by z minus a, right? This is something by z minus a plus something by z minus a square plus etc. The coefficient of 1 by z minus a, that is C1, is by definition the residue. So residue of a meromorphic function at a point A is, you take the principal part at that point. What is by my definition of principal part? It is that part which when you subtract from f. So our definition of pole was there is such a thing which if you subtract, it's a holomorphic function. So take the principal part and take the C1 coefficient, the first coefficient. So this is the minus first coefficient, so to say. And this was the definition of residue. First question is this well defined? What does this mean? So why is this true that this definition makes sense? Can someone quickly tell me?
The parts, they must have the same coefficient of.
They must have I think the voice is breaking.
They must have the same coefficient C1.
Why? Yeah, that's what.
I mean, that is the definition of well-defined is what I was saying.
Correct. So if I take Q and Q prime, they should have the same coefficient, -1 coefficient. That is well defined. And why is that true?
Suppose if Q and Q prime have M and N,
Yeah,
then we can take the maximum of that and we can clear the denominators.
yeah,
And then by uniqueness of power series, it will
correct. So
follow.
F minus Q and F minus Q prime are both holomorphic and then they will coincide, right? So, right, that's what you said, no?
Mm, I mean, I was saying clear the denominators as well so
Is
that we get
M
in a
equal,
power series form.
that is to assume M equal to N, right? If Q has up to M and Q prime has up to N, you can assume that M equal to N by clearing the denominators, right?
Yeah, or I was just saying that just take the maximum and then clear and then both things will follow at once.
Correct, correct. Yeah, correct. So take the maximum and clear the denominators, and then you will get power series. Uh, yeah, so Q may have some coefficient, minus first coefficient. Q prime may have some other coefficient to start with, but by clearing out, you are getting two power series expansion around A. Therefore, they should have all the coefficients same. In particular, this coefficient to be the same. Correct. Yeah. So this is well defined. So residue is well defined. Note that if gamma is a cycle and A is outside gamma star, then you can integrate Qz over gamma and normalize by 2 pi I. And this is nothing but C1 times the index of A over gamma. That's obvious, no? Because integral Qz will be integral of summation Ck by z minus a power k. But 1 by z minus a power k has a primitive unless k equal to minus 1, unless k equal to 1. Therefore, all the other terms except k equal to 1 will be 0. And at k equal to 1, 1 by z minus a dz is what is called the index with respect to gamma. So, and the coefficient is C1. So, this integral is C1 times the index. That's obvious. And C1 is by definition the residue of Q at A. Right? Residue of Q at A is C1. So, integral of the principal part is the residue at A times the index at A. This is an obvious computation because all other terms have a primitive and therefore the integral is 0. Right? Once you have a primitive, then the integral is 0 by fundamental theorem of calculus, one variable calculus, real one variable calculus. Okay, so now let's start the residue theorem. And what is the residue theorem? Again, you have done this before. So suppose f is a meromorphic function in omega, and let A be its set of poles. And if gamma is a cycle in omega minus a, after all, A is singularities. I don't want my cycle to go through that. So in omega minus a, if you take a cycle and assume it is homologous to 0 in omega, my residue theorem is going to be a corollary to Cauchy's theorem, global Cauchy's theorem. So we will manufacture a function and apply global Cauchy theorem. That will be the proof of residue theorem. So in order to do that, assume it is homologous to 0 in omega. And then the result is 1 by 2 pi I integral gamma fz dz is sum over the set of poles residue of f at A times index of A with respect to gamma. So the first observation to make is that this sum is happening. So this looks like an infinite sum because the set of poles may be infinite. But the first observation is that the only points that matter here are that is finite. So those points where the index is non-zero, because if index is 0, that then disappears. If index is non-zero, if you take a point such that the index is non-zero, then such a set, that set is finite. Therefore, this is actually a finite sum. Therefore, summing up is not a problem. So why is this set finite? This set is finite because so you take gamma star, right? That's a compact set and that divides C into components. And in the unbounded component, index is 0. You know that. That's a property of the index. In the unbounded component, index is 0. So if A is a point from the unbounded component in C, created by gamma star, then the index is 0 throughout there. Therefore, if index is not 0, that has to be contained in the bounded components. So in particular, it's inside a bounded set, and the set doesn't have a limit point, therefore it has to be finite. Right? So you are taking set of poles, and if you are taking a point where the index is not 0, it has to be in a bounded component. So B is contained in a bounded set, and poles do not have limit point. Therefore, this B has to be a finite set. So the sum on the RHS is finite. So we can enumerate. It's a finite set. So let A1, A2, etc., AN be this set, and let QI denote the principal part of F at AI. QI denote the principal part of F at AI, and then we are going to adjust this F. So take G to be F minus the sum of, so it's a finite sum of principal parts. QI is principal part at AI, and you take this. Now you know that F minus Q1 is holomorphic at A, meaning removable singularity at A1. F minus Q2 is removable singularity at A2. In particular, this particular G has removable singularities at A1, A2, etc., AN, right? By subtracting Q1, A1 has become a removable singularity, and Q2, etc., are anyway holomorphic at A1, right? Q2, the only pole is, only singularity is A2. So at A1, it's holomorphic. So this function G is has removable singularities at A1, A2, etc., AN. So throughout B, G is holomorphic. So by global Cauchy's theorem applied to this function G, and we are going to apply it to on the open set. From omega, you throw away the poles, so that's open, and you put back these poles, these n many poles, B. So that's still an open set, and that's where we are going to apply Cauchy's theorem. So you are removing exactly those poles where the index is 0. Okay, leaving those poles where the index is non-zero. That is B. So by Cauchy's global Cauchy's theorem, because the homologous to 0 condition we had for gamma, and therefore integral of gz dz is 0. Right? This is Cauchy's theorem because we have removed the singularity, so it's holomorphic. So Cauchy's theorem applies. Integral gz dz is 0, and therefore integral fz dz is, right? Integral of g is 0. Therefore integral of f is nothing but sum of integrals of q. Sum of integrals of qk. But what is integral of qk? We have already made this observation that integral of q is residue of q at a times the index of a with respect to gamma. So each of this is integral qk is residue at qk at ak times index of ak with respect to gamma. This was that elementary observation from earlier, because all other terms have primitive and fundamental theorem of calculus. So this we already know. Now this equals, observe that what is residue at qk, residue of qk at ak and residue of f at ak are same, right? By definition, what is residue of f at ak? You take the principal part qk and subtract qk and consider the c1 coefficient. Consider the minus first coefficient. And for qk, it is of course c1. For this also it is c1, because other things will not change that. The expansion around A1, Q2, etc. will not play a role in that. So again, as Aryaman said, by cross multiplying, you can see that. So this is nothing but residue of f at ak times, of course, the index of ak, and this is sum of a in a, residue f at a, index of a, because when a is in b, this is sum of a in b, this thing, but if a is in a and outside b, then the index is 0, therefore it is this sum. Index is non-zero specifically for b, and this is summing over b. So summing over a is also correct, because outside b index is 0, so it's okay. So I think this is all that we will do today. We have some time, so it's almost 10:30. We have a lot of time now. So you can ask me questions if you have, otherwise we will stop. Okay, anyway, let me stop this recording.